Welcome to this presentation and wish you a happy weekend. Last time we stopped on question 28. Today we are starting on question 29. Question 29 is saying explain the zero law for thermodynamics. Let's see the answer. Zero law of thermodynamics states that two systems in thermal equilibrium with a third system separately are in thermal equilibrium with each other. If you have two systems which are in thermal equilibrium separately, each separately with a third system, that means that these two systems are also in thermal equilibrium with each other. Consider a system. We have a system A and a system B, and A is separately in equilibrium with C. B also is in thermal equilibrium with C. The zero law of thermodynamics says that the A and B will also be in equilibrium. If we are considering the system A and B as two gases separated by an adiabatic wall. So this is an adiabatic wall. So this adiabatic wall is a kind of an insulator, an insulating wall, and it does not allow the flow of heat from A to B. But because A is in thermal equilibrium with C and B is in thermal equilibrium with C, the A and B will also be in thermal equilibrium. And this means that the temperature in A will be equal to temperature in C. So the temperature in A will be equal to temperature in C. Temperature in B will be equal to temperature in C. Temperature B will be equal to temperature C. Also, temperature A will be equal to temperature B because A will be in thermal equilibrium with B. That's what zero law of thermodynamics says. Let's see question 30. Question 30 is saying, explain the first law of thermodynamics. Explain the first law of thermodynamics. That is question 30. Let's see the answer. What is the first law of thermodynamics? The first law of thermodynamics is also called the law of conservation of energy. This law says that the energy of the universe is constant. It states that the energy of the universe is constant. This law is also called the law of conservation of energy. Energy can be converted from one form to another, or from one state or type to another, but can be created nor destroyed. It cannot be neither created nor destroyed. The first law of thermodynamics, it's law of conservation of energy, and deals with the conversion of energy from one form to another, or from one type to another. When we are talking about from one type to another, that means energy can be converted from potential energy to kinetic energy, or can be converted from one form to another. One form to another, we have different forms. Form of energy like chemical energy, we have gravitational energy. So energy can be converted from one form to another. We have sound energy, we have the radiant energy, and so on. So energy can be converted from one form to another, but it cannot be created nor destroyed. The energy can be neither created nor destroyed. There is a conservation of energy. Only energy is converted from one form to another, and it is conserved. The energy of the universe is conserved. That's what the first law of thermodynamics says. Energy, when you supply the energy which is Q, the energy which is supplied, it is going to increase the internal energy. It is partially increasing internal energy, and also it is going to perform the work on the environment. That means that the energy that is supplied as Q, half of it, or not half of it, a part of it, it is going to increase the internal energy, while the remaining is going to contribute to the work on the environment. What is internal energy? Because we are saying that the heat that is supplied, the energy that is supplied, increase the internal energy and also contribute to the work. So what is internal energy? Internal energy is the total energy of the system. You have the system, is the total energy of the system, and this energy is due to the motion of molecules. Molecules are moving, the vibration of atoms, the electrical energy within the atom, and the energy is stored in all chemical bond within more molecule. That's what we call the energy, the internal energy. Internal energy of the system is the energy due to motion of molecules, vibration of atoms, the electrical energy of atom, and the energy stored within the bonds. The bonds in the molecule. That's what we call the internal energy. But internal energy does not include the motion of the system as a whole. If the system is moving, the internal energy does not include the motion of the system as a whole. It does not also include the external force field, the energy contributed to the external force field. So, because the internal energy is just internal, the total energy internal inside of the system. This energy is due to the motion of molecules, the atom vibrating, electrical energy in the atom, and the energy stored only in the chemical bonds. If the system is doing the motion, or there is the external factors, external force field contribute to the energy, that is not the internal energy. The internal energy is only internal. It is due to the vibration of molecules, the atoms vibrating, electrical energy of atoms, and the energy in or chemical bond within the molecules. That is internal energy. So internal energy of the system, because it is internal, it can be changed either by a flow of work, heat, or both. So when you have the change in internal energy is equal to the Q, which is the heat, and the plus the work done. The only internal energy of the system can be changed by either the change in heat or the change in work. When there is a work which is done, when there is the heat which is moving outside the system, or work done which is done by the system, or a system outside the system is doing the work on the internal energy. So here we are changing the internal energy of the system. Internal energy can be changed by a flow of work, heat, or both. This is the formula for internal energy. Internal energy is equal to Q plus C plus work done. If an object moving, if an object is moving, that means it has what we call kinetic energy. But when an object is moving, its potential energy is converted to kinetic energy. And this kinetic energy becomes zero when an object hits the surface. When an object is moving, you have the potential energy which is converted to kinetic energy, and when it is coming to ground, that kinetic energy becomes zero. So we are giving example of converting the energy from one type to another. So potential energy can be converted to kinetic energy. A second example of converting the energy from one form to another is when you have fire burning in your fireplace. So that means the chemical energy in the wood or in a biomass, it is changing into thermal energy or heat energy or radiant energy in the form of light energy. Another example is when you have chemical energy in fuel. So we have a fuel that we are using to drive our car. So when you have the gasoline or natural gas, so in fuel, as a fuel, so it is converted into mechanical energy so that the car can move. So you have gasoline or natural gas, so it is chemical energy which is converted to mechanical energy, so that the car can move. So energy is conserved. Only energy is converted from one type to another or one form to another. When you have a book at the edge of the table, it has a gravitational potential energy, and when it falls, the book is knocked off the table, the potential energy is converted to kinetic energy, then the book is going to move. Once it is hitting the ground, the kinetic energy becomes zero. Then, so when the book hit the ground, some of the energy becomes thermal energy due to collision with the ground, and the other energy, the remaining energy, transformed to sound energy. So that's why you can see when the book is falling, there is a collision to the ground. That collision will give thermal energy, and also you will hear the sound, and that sound, that's what you call sound energy. So energy is a conserved, energy is converted from one form to another, but energy can neither be created nor destroyed. So we are still in the first law of thermodynamics, which say that the energy of the universe is conserved. When you have the falling water, you have the kinetic energy of falling water, and it's transformed into mechanical rotational kinetic energy that used to turn a turbine. So in a turbine is you have hydropower, you have the falling water, which is having kinetic energy, and it is converted into mechanical rotational kinetic energy by turning the turbine. So this mechanical rotational energy that is created is converted into electrical energy by way of a generator. So you have a generator which converts mechanical rotational energy to electrical energy. And this electrical energy can be converted into another form of thermal energy by using a resistor. So, and it can be used to heat a house. Another example is when our body burns sugar during exercise. When you are doing exercise, so you are burning the sugar, and the chemical energy in the sugar is changed into mechanical energy that you use for doing your exercise, and also it is converted to thermal energy to heat your body. Let's go to question 31. Question 31 is saying, consider a thermodynamic system absorbing 300 joules of heat and performing 500 joules of work. Calculate the change in internal energy for this thermodynamic system. So internal energy is equal to Q plus C, work done, the heat plus work done. And here, a thermodynamic system is absorbing heat, which is 300 joules. That means the Q is positive, because the system is absorbing the energy. And here it is performing 500 joules of work. That means that the system is doing the work. There is a flow of work from the system. That means that the work done will be negative. Now let's use the formula to calculate the internal energy. Internal energy is equal to Q, which is the heat plus the work done. The heat was given as 300 joules, but because the system is absorbing the heat, the system is gaining the heat, the Q will be plus 300 joules. Then we need to add the work done. The work done, here they are saying the system is performing 500 joules of work. That means that the system is losing the work, is doing the work to the surrounding. There is a flow of work from the system. This means that the work done will be negative. By doing so, we have the change in internal energy is equal to Q plus the work done. So we have 300 joules minus 500 joules. Then we will be having the internal energy, which is equal to minus 200 joules. Let's go to question 32. Question 32 is saying a thermodynamic system is absorbing the heat of 720 joules. We have 720 joules, and it is the thermodynamic system which is absorbing the heat. That means this one will be positive. The Q will be positive because the heat is absorbed. There is an addition of heat to the system, and the surrounding perform 300 joules of work on the system. That means that it is the surrounding which is performing the work on the system. That means here the work done will be positive, there is a flow of work from the surrounding to the system. So here also we have the positive work. Calculate the change in internal energy of the system. So here also we use the formula. The formula internal energy is equal to Q plus work done, the heat plus work done, which is equal to 720 joule plus 300 joule. Then you have 1020 joule. Let's move to question 33. How much work is required to compress a monoatomic gas? We have a monoatomic gas that is going to be compressed at the pressure of 2.5 times 10 power 5 Pascal. From initial volume, you have initial volume from 0.015 meter cube to a final volume of 0.01 meter cube. Here we have a compression from 0.015 to 0.01 meter cube, and the compressing is done at a constant pressure of 2.5 times 10 power 5 Pascal. What is the change in internal energy if the system releases 300 during this process? Here we have the heat, but it's the heat that is released. That means here the heat will be negative. A system is releasing the heat. In this case, heat is negative. Q is negative in this process. So we know that the internal energy is equal to Q plus work done. We have the Q, but is also negative. But from the pressure and the volume, we are going to calculate the work done. So the work done is equal to minus PdV. So minus PdV, the pressure times the change in volume. If we can then substitute the value, we see work done is equal to minus P minus 2.5 times 10 power 5 Pascal. The change in volume, the final volume is from 0.01, the final volume, and the minus the initial volume is 0.015 meter cube. So here we are doing the change in volume. Then we get 1250 Pascal a meter cube as the work done. So let's convert this into joule. So we know 1 Pascal is equal to kilogram per meter second square. Here then if you are taking the Pascal multiplying for meter cube, then if we need to multiply meter cube here, that means meter cube will cancel with m to remain with meter square. So then we will get a kilogram meter square per second square, which is joule. So that means that this 1250 Pascal meter cube will be equal to 1250 joule as work. So the work is positive because work flow into the system. We are compressing. If you are compressing the system here, it's obvious that we are compressing. The work is done from the surrounding to the system. The work done should be positive. So let's then calculate the internal energy. The internal energy will be equal to Q plus work done. The Q will be negative because the system is releasing the heat. Then plus the work done, which is positive. So we'll get 950 joule as the internal energy. Let's move to question 34. Question 34 is saying a balloon is being inflated to its full extent. So by heating the air inside it. So there is an extension of the balloon, inflation of the balloon. In the stage of this process, the volume of the balloon changes from 4 times 10 power 6 liter to 4.5 times 10 6 liter. So here the balloon is increasing in volume. There is an expansion of the volume. There is an inflation of the balloon. So by the addition of 1.3 times 10 power 8 joule of energy. So here we are adding the energy. Adding the energy means that Q will be positive because we are adding the energy as heat. Assuming that the balloon expands against a constant pressure of 1 atmosphere, the pressure was given. Calculate the change in internal energy of the process. We have the pressure and you have the volume. So that means the change in volume. If you have the pressure and change in volume, you can calculate the work done and the heat was given as this one and is positive. Then they are asking to calculate the change in internal energy of the process. So we need to calculate first the work done, which is equal to minus PdV minus 1 atmosphere, which is the pressure, then times the change in volume. So we get this 1 liter atmosphere. Then we need to convert this liter atmosphere to joule. To do so, we need to divide the two constants, the R constant in joule per mole Kelvin, dividing with R constant in liter atmosphere per mole Kelvin. Then we will get that 1 liter atmosphere is equal to 101.3 joule. Then if 1 liter atmosphere is equal to 101.3 joule, then minus 0.5 times 10, 6 liter atmosphere will be minus 0.5 times 10 power 6 liter atmosphere will be equal to minus 0.5 times 10 power 6 liter atmosphere times 101.3 joule per liter atmosphere. Then we will get minus 5.065 times 10 power 7 joule as a work. After getting the work, then we can calculate the internal energy. We know that the internal energy is equal to Q, which is positive because it is the heat added. Then the work done is negative because we are doing a expansion of the baron, inflation of the baron, minus 5.065 times 10 power 6 joule. Then we get 7.935 7.935 times 10 power 7 joule of internal energy.